In this video, we'll be discussing section 4 of chapter 4, uniform circular motion. What is uniform circular motion? Let's imagine an example of uniform circular motion. For example, this ball spinning around on this roulette wheel. The ball is moving around in a circular path at a fixed radius that we could define as r. We can think about lots of other examples of circular motion. Satellites in orbits or balls at the end of strings that were spinning around. Any kind of motion where I have an object that is moving in an orbit or in a circular path around a fixed position. Circular motion is another example of two-dimensional motion, motion in a plane. I can't use a single direction to define an object that's moving around in a circle. Let's focus on a particular type of circular motion, uniform circular motion. What do we mean by uniform circular motion? Well, now in addition to being in circular motion, it's also going to have a constant speed. The object is moving in a circular path with a fixed speed as it makes its way around the circle. So it's not speeding up or slowing down, it's just maintaining a fixed velocity. So at any point, if I draw the velocity vector, the velocity vectors have the same size, and they circulate around this circular path. In this example, the time interval, right, there's some amount of time that it takes for this object to make it one revolution or one time around the circular path. And we're going to call that particular time big T, or the period of motion. We can see here that the period is related to the speed. I could measure the circumference, right, the total distance that I travel when I make one circular path. And if I divide that by the period, the time that it takes to make that circular path, well, then I should have that speed that the object has at any instance in time. This is a distance divided by the time that it takes my object to cover that distance, and so I get the speed that the object has to be traveling with during this motion. Let's also define an angle. So I'm going to define an angle theta with respect to the positive x direction that's moving in the right. Positive values of this angle are going to go in the counterclockwise direction. So if I consider a particle at some distance r away from the origin of this xy coordinate system, I can find this angle theta, and there's going to be this quantity that's called s that I'm going to call the arc length. It's the distance, right, the total distance of this curved path that I travel while I'm in circular motion to open up this angle theta. That angle can be measured in degrees, revolutions, or radians. Very typically, though, we're going to use the radian units for our calculations here, but we have this handy conversion that we can use to move between the different ones. And so we can see if the angle is measured in radians, then there's a simple relationship between theta and that arc length s. That arc length s is just r times theta. Think about an example that you know that's familiar to this. If I take this angle theta to be 2 pi, that's the entire revolution of a circle. I go completely around in 2 pi, 360 degrees. If this is 2 pi r just gives me the circumference. And you know if I go once around the circle, then this arc length should be the circumference. So this is like, this is the same equation that gives us the circumference, but this just gives us that arc length for any opening angle theta I have for a circular path that is some distance r away from my origin or the center. Now I'm going to define another quantity. I'm going to define something that I'm going to call the angular velocity. Imagine I have this particle on a circular path, and it's moving through an angular displacement. So I know that it starts at some position here around the circular path, and I'm going to say where it is in terms of this initial angle with respect to the positive x direction. So it starts at position theta I. It's always at the same distance away from the origin, so I can specify where along the path it is just with the angle. And then sometimes later, that angle is now theta f. I can write the angular displacement as just the difference between those two angular positions. And those unfold in a time interval of delta t, just t final minus t initial. In the same way that we defined a velocity, a linear velocity in previous chapters, we can now define an angular velocity. It's just going to be the change in that angle divided by the time interval. And in an identical way to how we describe the instantaneous linear velocity, we can imagine shrinking that time interval down to 0 to define what we call the instantaneous angular velocity. It's just the time derivative of that angle theta. Okay? So if that angle theta has a functional form with respect to t, I could take the time derivative to know the instantaneous velocity at any point, angular velocity in this case. Notice that the units of angular velocity here, theta is in radians, t is in seconds, so that average angular velocity has units like radians per second. Angular velocity, we're going to use this symbol omega to represent the angular velocity, is the rate at which a particle's angular position is changing. We're going to use a sign convention here. As shown in the figure, this angular velocity can be positive or negative. If it's positive, it means that the object is rotating in the clockwise direction, and if it's negative, it means that it's in the counterclockwise direction, and a negative omega means it's rotating in the clockwise direction. And a particle moves with uniform circular motion if omega is constant. So if it has a fixed omega, it's just rotating around with that fixed omega, and it does that for all of time. Omega, in exactly the same way we saw for the relationship between velocity and position, is just the slope of the theta versus time curve at some given times t. And so therefore I can write a kinematic equation that says that the final theta position, angular position, is equal to the initial position plus the area under the omega v curve, or just theta I plus omega delta t. Look, this looks like the same kinematic equation we saw for one-dimensional motion. Instead of it saying Vx plus V delta t, it says omega plus, right? This is my velocity term now. The thetas are my positions around the circle, and omegas are my initial velocity, or like my initial velocities. When the angular velocity is constant, this is uniform circular motion. In this case, the particle goes around the circle one time, and its angular displacement is 2 pi during that period t. So I can see that that magnitude, that speed, that angular speed, the magnitude of the angular velocity has to just be 2 pi divided by that period. So I can define the period as 2 pi radians divided by omega for uniform circular motion. The tangential velocity component, delta t, is the rate, ds dt, at which the particle moves around the circular path. At any instance around that circular path, its velocity is pointing tangential to its trajectory. So the tangential velocity and the angular velocity are related together. Okay. They're related together, right? Remember, s was just theta times r. And so r is some constant. It's going to pull outside of this. And so now when I take the derivative of theta times r, I just get the time derivative of theta with respect to t times r, or omega r. So I can relate that tangential linear velocity to my omega through this equation just by scaling by the radius of my circular path. And in this equation, we can check the units. The units of v better be meters per second, whereas the units for omega we said were radians per second. So here I have radians per second times meters. Radians meters per second. Notice that radians, therefore, actually have to be unitless quantities. Those angles are actually unitless, and radians is just the way that we express the unitless quantities that we're counting up as we move along that circular path. Okay, that ends our initial discussion of circular motion. Thank you.